all, this question pertains to electromagnetic theory and it was asked in Electrical Engineering GATE 2020 paper. And this question basically gives us the electric flux density given as in this equation, and we are required to find the total electric flux in coulombs, basically the charge emanating from the volume enclosed by a solid cylinder of radius 3 meters and height given as 5 meters, oriented along the z-axis with its base at the origin. These are the options given. So to solve this question, we need to refer to the lecture 58, Gauss divergence theorem from IIT Kharagpur. So this is some of the useful data which we need to keep handy before solving this question. The first one is the Gauss theorem, which states that the surface integral of a vector field, in our case which is the electric flux density d, the surface integral of the vector field gives the, that is this d, will give us the total charge enclosed within that surface area. In our case, we have been given the surface area of a cylinder. So this is the axis y, x-axis, z-axis. Let's say this is our cylinder area. Sorry, this is our cylinder. So this radius is 3 meters and the height of the cylinder is 5 meters as given in this question, and we are required to find out the total charge enclosed within this closed surface area. Now we know that the Gauss divergence theorem relates the closed surface integral of a vector field to the volume integral of the divergence of that vector field, which in our case is the electric flux density. So this we can use, we can integrate the divergence of the electric flux density d, we can find the volume integral, and hence we can find the enclosed charge. Another thing which we need to know is the del operator in the cylindrical coordinate system, which is given according to this equation. This is the formula. So let's get started with the solution. The very first thing, the Gauss theorem. It states that d dot ds surface integral gives the charge enclosed within that surface, and according to Gauss divergence theorem, so the surface integral is basically equated to the volume integral in the Gauss divergence theorem. So to find out this, we can use the volume integral because we have been given a closed surface which forms a finite volume, and hence we can use this theorem to find out the charge enclosed. So for this thing, we need to find out the divergence of this electric flux density. So now we'll have to find out del dot d, and that too in the spherical coordinate system, which is nothing but 1 by r, 2r, dou by dou r of r into dr plus 1 by r dou by dou phi of d phi plus dou by dou z of dz. dr, d phi and dz are the components of the electric flux density in the spherical coordinate system. So now putting the values, we will get 1 by r dou by dou r. This is r into 15 plus 1 by r dou by dou phi. This is nothing but 2r plus dou by dou z. This is nothing but minus 3rz. This is given as 15 by r minus 3r. So this is the value of del dot d which we have found. Now this we have to substitute in that equation. Let's do that. Volume integral of del dot d dv is equal to volume integral 15 by r minus 3r r dr d phi dz. This is the elemental volume dv in spherical coordinate system. Let's separate this two parts. The first one will be 15 by r into r dr d phi dz minus integration of 3r into r dr d phi dz. This will be charge enclosed is equal to integration of 15r dr 15 dr d phi dz minus 3r square dr d phi dz. Now this will not be equal to nothing but r. Now what is the, we'll put the limits of these variables. For r it is nothing but 0 to 3 meters. The radius was given. For phi we are spanning the entire cylinder, so it will be 0 to 2 pi. And z will be the height, that is from 0 to 5 meters as given in the question. Similarly, same goes for this 3, 0 to 2 pi and 0 to 5. So this will be r 0 to 3 into 5 0 to 2 pi into z 0 to 5 minus, this is nothing but r cube 0 to 3 5 0 to 2 pi into z 0 to 5. This will be nothing but 15 into 3 into 2 pi into 5 minus r cube is nothing but 27 into 2 pi into 5, which is nothing but 180 pi. So this is the final answer highlighted here. This is the final answer. To get more insights on this solution, refer this lecture. Thank you.